Hey there, everyone. This is Jumpgate here. I'm joined with Erik and Dr. Oleg Abramov here. And we are so excited to have you on the stream, Doctor.
Thank you.
How's everybody in the audience doing today? Let you filter in for a second while we get this team started. How's your day been today, Doctor?
Fantastic. Thank you. I've actually been here for 3 days working with the Million on Mars team.
Yeah, that's fantastic. It's been so great to have you. Been very fortunate to have you over the last 3 days, educating us and enlightening us in your work.
I really enjoyed the experience. Thank you for hosting me, especially Erik and Carrie and Joel.
Yeah, thank you so much, sir. So we're going to go ahead and we're going to just go ahead and kick off with your presentation, sir. So we'll go ahead and get your desktop screen on here. And once you're once you're ready, sir, we can go ahead and we can start.
Okay.
Give you the floor.
Fantastic. I can start now?
Yes, sir.
All right. Hello, everyone. My name is Oleg Abramov. I am a planetary scientist at Planetary Science Institute in Tucson, Arizona. And a lot of my research has been on Mars. And I actually spent a total of 5 months in simulated Mars environments, a total of 1 month at MDRS, which is an installation run by the Mars Society in the Utah desert, and 4 months at high seas on the upper slopes of Mauna Loa in Hawaii. I've been a player of Million on Mars since day one. I'm very excited about the game and its potential. I'm here partly to help bring in actual data from robotic spacecraft that are exploring Mars and help integrate that data into the game to make the game more realistic, and with the hope that eventually we can integrate some kind of a citizen science experience into the game and have the players potentially solving problems that are relevant to real Mars science exploration and settlement. Today's presentation is on SpaceX Starship, and earlier today, actually, we spent a fair bit of time on the Million on Mars roadmap for aerospace, and the vehicles that are involved in this roadmap are derived from the Starship. They're based on the Starship, and I'm very excited about this roadmap and its potential. So in today's presentation, I'll talk about SpaceX Starship, provide kind of a description and update of where SpaceX is at with their development, and talk about planetary missions that could be enabled by the Starship, and talk about one of the planetary missions that I'm involved in. So I'd like to start with this chart that shows the total mass that was launched to orbit in the second quarter of this year by various launch providers. And that's probably the best metric to evaluate which launch provider is the most efficient. So as you can see from this chart, SpaceX absolutely leads the pack here. In fact, they have delivered more mass to Earth orbit than anyone else, including China, Russia, United Launch Alliance, which is a major US company, Europe, and various smaller launch providers.
That's incredible. It's like that little call-out graph. It's like astonishing. You got first excited about India, and then you look like, oh wait, that's way down there in the noise.
Yeah, exactly. Yeah, it's a zoom in. Yeah, starting with India, then Rocket Lab, then Korea, and so forth. And I also want to say that this is not a statistical aberration. This has been the case for several previous quarters. Basically, SpaceX has launched more mass than anyone else, or in fact, everyone else combined. This chart is also really interesting. It shows the total number of spacecraft that have been launched to Earth orbit by a launch provider. And SpaceX leads here with 473, followed by China and Rocket Lab at 36 each. Now, SpaceX does launch a number of small spacecraft, specifically Starlink, so that affects the statistics. But it's still interesting to see just how big of a difference is between SpaceX and everyone else. This chart shows the launch history of SpaceX in terms of number of launches per year. Different colors here mean different things. Green is Falcon 1, which is the first vehicle that SpaceX developed. And then that transitions to Falcon 9. Dark blue is new Falcon 9, and light blue is used Falcon 9. And yellow here is Falcon Heavy, which is a derivative of the Falcon 9. And orange are the failed launches. And overall, looking at this graph, you can see a very clear trend that appears to be exponential in terms of number of launches per year. And the white here are planned launches for the remainder of the year. So they have already had a record year, and they have more launches planned. SpaceX Falcon 9 is in many ways the key ingredient to this success. The key technology is the reuse of the first stage, which can land on both land and on ocean platforms. So far, Falcon 9 had 178 launches, 140 booster landings, and 117 booster reflights. Current record for the number of flights by the same booster is 13, and that's shared by at least two different boosters, I believe. The current record for the fastest booster turnaround is 21 days, and there are two major planetary missions that will be launched on the Falcon Heavy, which is a derivative of Falcon 9, and those missions are Psyche, which is going to a metal asteroid, the first mission to a metal asteroid, in fact, and Europa Clipper, which is a mission that I'm a co-investigator on, and that's launching in 2024. So I'll talk about Europa Clipper next, and we'll get back to Starship. Europa Clipper is a mission to Europa, which is a satellite of Jupiter. It has three main objectives, which are to study the geology, composition, and ice shell and ocean of Europa. Europa is an ocean world that is covered by an ice shell that is approximately 10 kilometers thick, but we don't know exactly, and that's one of the things that this mission will help us find out. And it will thoroughly map the surface geology, surface features, including sites of recent or current activity. There have been some venting on Europa that was observed by Hubble Space Telescope, and that will be of very high interest. And this mission will also map the chemical composition of the surface and the surrounding environment. This shows an animation of what the mission will look like. So in the center here is Jupiter. Blue circle here is Europa Orbiter. So the Clipper will orbit Jupiter and will do repeated flybys of Europa, diving into a hostile radiation environment for a short time, gathering data on Europa, then coming out of that radiation environment and transmitting that data to Earth. And it will do a lot of these orbits. Some of the things that we're hoping to find out about Europa from this mission. One of the major uncertainties right now is exactly how thick the icy crust of Europa might be. The model on the left here is a thin icy shell model, where the icy shell is only a few kilometers thick, and in parts it's being melted by plumes of warm water that are driven by volcanic eruptions on the ocean floor of Europa. The floor of Europa is basaltic, much like the Earth's ocean, and it most likely has volcanic activity due to tidal heating from Jupiter, and we see surface expressions of this activity in areas where ice appears to have recently been molten, and we also have venting at the fissures on the surface. On the right is a thick shell model. So here we have an icy shell that's maybe a couple of tens of kilometers in thickness. That's also driven by the heat from the ocean floor. This heat drives convection within the ice itself and results in lenses of liquid water within the ice and also some surface activity. And with Europa Clipper, we'll be able to measure exactly how thick the shell is using more than one method.
I got a couple questions for you back there. It's a really exciting,
Yeah.
exciting slide. Do you have a gut intuition yourself if it's thin ice or thick ice?
That's a good question. I think given the amount of surface activity that we're seeing and how young the surface is, I'm probably leaning more towards the thin ice model, but it's probably my best guess would be it's somewhere in between these two extremes. So I would probably bet on average of 5 to 10 kilometers with areas that are significantly thinner. And those are the areas that we're most interested in because they might provide a way to access the ocean. Europa is very interesting because it's a potential place for life. It has more liquid water. Total amount of liquid water on Europa is actually larger than on Earth. Conditions are very similar to deep ocean environment on Earth. Average temperature of the ocean is between 0 and 4 degrees Celsius, but it would be significantly warmer near areas of volcanic activity. It has a benign radiation environment because the icy crust would block charged particles. And it has an Earth-like chemical balance and Earth-like composition of the seafloor. It probably has hydrothermal activity on the seafloor, similar to what we call black smokers on Earth, that are potential sites for the origin of life. And this has been simmering in a relatively stable configuration for over 4 billion years. So it would be really interesting to get down there and see what cooked up, if anything.
So if it has more liquid water than Earth, are you saying that if there's life on Europa, then the biosphere on Europa would have more total volume than the biosphere on Earth?
Potentially, yes. It depends on how you count. If you count total biomass, that is potentially possible, yeah, because there's
I was talking about the volume, right? The volume of,
yeah.
You said there's more liquid water, so the volume of water is bigger.
Yeah, exactly.
That's a crazy idea. I never thought about the biosphere on Europa being larger than Earth.
Yeah, that's possible. It's one of the possible outcomes of this.
Wow.
So Europa Clipper has a number of instruments. Some of them will sample the ocean directly by flying through the plumes that are coming out of the fissures in the surface. So it's basically water vapor, water coming from the ocean that would allow us to directly measure the composition of the ocean. It also has a spectrograph and a spectrometer that will allow us to measure the chemical composition of the surface. Multi-camera system that will map Europa in 3D in full color. It has an ice penetrating radar that will directly confirm the presence of the ocean and measure the thickness of the icy shell. And the instrument that I'm on is called eThemis. It is a thermal imager, and its primary purpose is to search for hotspots or areas of elevated temperature on the surface. And it will also map the temperatures, both day and night temperatures of the surface. ETHEMIS is derived from an instrument called THEMIS, Thermal Emission Imaging System, that flew on Mars Odyssey. Mars Odyssey was launched in 2001 and is still operational. ETHEMIS will measure and map surface temperatures. It will detect anomalously high temperatures or hotspots. And this is particularly interesting because such locations might be potential sites to access the ocean in the future. This is what the expected temperature mapping looks like. On the left is a thermal image from THEMIS showing temperature distribution on the Mars ice cap. On the right, here we have a visible light image of a fracture on the surface of Europa. In the middle here, we have some of the best resolution that would be expected during close flybys. And on the bottom here, we have a resolution, basically an average resolution that would cover most of the surface of Europa. And now, as I said, the really interesting part of this mission is finding locations where the ocean might be accessible. In the future, it may be possible to use a power source to melt through the icy shell of Europa and deliver a submersible vehicle to the Europa Ocean. Such a mission would probably be quite heavy, and it's uncertain if any of the current launch vehicles would be able to get it to Europa. And here I'll segue into a Starship and how it might be able to help. What is Starship? It is a new vehicle that's under development at SpaceX. It consists of a super heavy booster, which is shown here, and Starship, which is sitting on top of the booster. It is the largest rocket ever by height, weight, total thrust, and maximum payload. It's designed to be fully reusable, both the booster and the Starship, with a 24-hour turnaround target. So they're basically aiming for airline-like operations with this vehicle. One of the really exciting parts is that the initial price target per launch is about $10 million due to its full and rapid reusability. This is compared to a NASA space launch system, which is estimated to cost about $2 billion per launch, because the entire system the rocket is completely fully expendable. The primary design goal for Starship is to transport humans and cargo to Mars, but a secondary goal is to have it be a generalized transport mechanism for the greater solar system. There are variants for cargo and human missions to Earth orbit, Moon, Mars, and other destinations being developed. One really exciting development last year is a contract that was issued to SpaceX by NASA to develop a lunar version of Starship as part of the NASA Artemis program to deliver the next humans to the moon in the next 3 years or so. And right now, the plan is to work together with existing NASA hardware, including the Space Launch System and the Orion capsule. Although Starship should be able in the future to do this. Basically, you can do the entire mission with Starship. And regardless, it is now on the critical path of returning humans to the surface of the moon. A quick summary of Starship development history. Internal development started at SpaceX in 2012. Design and first test hardware was unveiled in September of 2016 at the 67th International Astronautical Congress. The system was previously had different names, including Mars Colonial Transporter, Interplanetary Transport System, and Big Falcon rocket. All of those refer to the same vehicle. The vehicle went through several iteration cycles. On the left is the version from 2016 as it was unveiled, and on the right is a version from last year, which is basically what we have now, more or less. And one of the biggest differences is back in 2016, they were planning to do a carbon composite vehicle, and that was later switched to a stainless steel vehicle, which turned out to be stronger and easier to work with and easier to develop. There have been a number of test flights with Starship. Flight testing began in April 2019. With the first flight of a Starhopper vehicle, which is pictured here on the left. There have been a total of 10 test flights with Starship vehicles, 10 test flights with 8 different vehicles up to 12,500 meters in altitude, using a hardware-rich, fast iterative approach, which basically meant building lots of prototypes, flying them quickly. They crashed a number of them, but they learned something from each iteration and they fixed it in the next prototype. This is what descent, flip maneuver, and landing of Starship looks like. We do a skydive through the atmosphere, flip maneuver, the engines light up, and the Starship performs a powered landing. One of the key technologies that enable Starship is the Raptor engine that has been in development since 2012. It powers both Starship and Super Heavy. It is the first full-flow staged combustion cycle engine, which is an extremely efficient cycle, but extremely difficult to make work. It is the first orbital class engine that uses that to fly. It is also the first methane orbital class engine to fly. It has the highest chamber pressure of any orbital class rocket engine at more than 300 bar, and it's designed for full and rapid reusability with minimal inspection. I'll go through some of the construction and launch infrastructure for Starship. Currently, this is their primary fabrication and launch site called Starbase. It is located in the southeast part of Texas, near the Mexican border. And here we have the launch site, and further away, the construction site. Taking a closer look at the launch site, on the left is the launch tower with the launch pad next to it. They refer to this entire complex as stage 0 because it performs a lot of the functions that traditionally were performed by the vehicle itself, like engine ignition, for example. So they're trying to make the vehicle as efficient as possible by offloading as many functions as they can to stage 0. This tower is really interesting because it has this mechanism called chopsticks that I will talk in the next slide, that is used both as a crane and as a mechanism to catch vehicles, both booster and the Starship, as they return to the launch site. This is a fuel farm for the launch, for the orbital complex. These fuel tanks were manufactured locally by SpaceX using the same technologies that they used for Starship and Super Heavy, basically the same manufacturing process. And on the right here is a suborbital testing area, and this is one of the Starship vehicles on one of the suborbital launch pads, and fuel tanks for the suborbital area here. Taking a closer look at the launch tower and chopsticks, as I said, they serve as a crane, as a surface structure, and as a stabilizer. And in this animation in the bottom left, you can see the Starship being lowered using the chopsticks. Here they're basically used as a crane. If you look carefully, you can see the chopsticks moving down the tower. At this point, both Starship and Super Heavy have been lifted and stacked by the chopsticks. Upper right here is the Super Heavy booster being lifted onto the orbital launch mount. Chopsticks will catch and restack Starship and Super Heavy after their flights, and this is what that looks like. Here is the booster Super Heavy coming back, being caught by the chopsticks, and then being lifted up onto the launch pad, onto the launch mount. And here, similar process with the Starship. The Starship returns, it briefly hovers, it's caught by the chopsticks, it's translated over to the Super Heavy and stacked on top of it. Moving on to the Starbase construction site, they have two high bays for vertical integration of Starships and Super Heavy boosters. Just north of those, there's an atmospheric processing area that's really interesting. This tower here is used to extract oxygen out of the atmosphere. So they have the ability to make liquid oxygen on site for their vehicles. And in the future, they're also planning to at least test out the process of producing methane from carbon dioxide and water, which is a process that would be very important on Mars to manufacture fuel locally. There are some prototypes of Starships and one Super Heavy booster here. These tents have been used for construction of segments for Starships and boosters, but they're being replaced by this building that's being built here. This is a permanent factory for constructing Super Heavy boosters and Starships, and eventually it's expected to occupy this entire footprint here, and it may be able to pump out one Starship and one booster per week once it's fully operational. So Texas is not the only place where SpaceX is building launch infrastructure. This is Florida, Cape Canaveral, Kennedy Space Center, Pad 39A. This is a very historic location for spaceflight. Almost all of the Apollo missions lifted off from 39A. Most of the shuttle missions, including the first shuttle mission, lifted off from this launch pad. And currently, it's the only place in the United States that can launch humans to orbit. And on the left here, you can see the tower that's being used for human launches and the walkway that's used by astronauts to board Dragon vehicles on top of Falcon 9s. But there is a lot of construction going on at 39A, and this is a launch tower similar to the one in Texas that's under construction. This is a very recent photo, and I think they're just one segment short of completion here, maybe two segments. And next to the tower is the launch pad. You can see the legs of the launch pad. That's also under construction. They're also building a Starship factory in Florida at Kennedy Space Center. On the top of this image is an existing SpaceX facility called Hangar X that's used for processing of Falcon 9 boosters. In fact, you can see one here. And this entire bottom area is dedicated to Starship. You can see that on the bottom here, footprint for a Starship factory, Star Factory under construction. And just north of this footprint, there will be a high bay here for vertical processing. You can also see a couple of segments for the tower that have since been transported to Pad 39A sitting here. And I have another picture of the same area that was taken about a month apart. And you can see a very significant progress in the area, especially on the factory in the bottom here. So I'll go back. This is July 31st, and this is September 8th for comparison. So very, very rapid progress at this site. First Starship orbital launch is expected within 6 months or so from Starbase, Texas. At this time, environmental approval has been obtained. They are still waiting currently on the FAA launch license. They are conducting static fire tests of Starship in the left here and booster shown on the right. On the first launch, they're planning to deploy at least one Starlink version 2 satellite, which is a significantly improved version of Starlink designed to be launched by Starship. And it's estimated to be at least 10 times more capable than Starlink version 1. During this first orbital launch, the booster may return to the launch site, or it may perform a controlled splashdown in the Gulf of Mexico. So if all goes well, there is a chance that we might see a return to the launch site and booster being caught by the chopsticks on the first flight. Starship would do one orbit around the Earth and perform a controlled splashdown off the coast of Hawaii. Initial applications in Earth orbit for Starship. Essentially, as soon as it starts flying, SpaceX is planning to use it to deploy large numbers of Starlink version 2 satellites. This animation shows how that is expected to be done. They have basically a slit, and the satellites will come out pass dispenser style. And this system has already been developed, and it's present even on the first Starship that's expected to reach orbit. Shortly thereafter, other payloads would be deployed to Earth orbit using Starship. They will be conducting orbital refueling tests in orbit and prepare for first human missions on Starship. There is a program called Polaris that will start with a couple of Crew Dragon missions, including the first private spacewalk, and that's expected before the end of the year, I believe. And it will culminate in the first human flight of Starship. Beyond that, there are plans for missions beyond Earth orbit. One is NASA human landing system demo that would demonstrate orbital refueling and automated lunar landing. That's expected no later than 2025. Orbital refueling is key to get beyond Earth orbit, and this is a technology that they will be working very hard to develop in the next couple of years. Then NASA Artemis 3, which is expected to be first human landing since Apollo, no earlier than 2025 currently. Another interesting mission is called Dear Moon, which is a privately funded mission to perform a lunar flyby on a free return trajectory. That's expected no earlier than 2023, although it's likely to slip. Dear Moon is really interesting because it's pushing Starship to the limit that is about as much as you can do without doing an orbital refueling. To enter lunar orbit, or to land on the moon, or to go to other places in the solar system, orbital refueling is necessary. First cargo flight to Mars, currently expected no earlier than 2024, and first human flight to Mars, they're aiming for no earlier than 2026. In terms of its capabilities for planetary missions, Starship can do a lot to enable really interesting robotic missions to planetary targets. Starship itself can serve as an instrument platform. Payloads can be separated from it and flown independently. Starlink version 2 can also potentially be used as a planetary instrument platform. In terms of total missions, refueling missions that are needed to fully fuel Starship in Earth orbit, the current number is around 8. It will probably be brought down somewhat as the system becomes more mature and more efficient. Starship is potentially carbon neutral because it uses methane as a fuel, which can be produced from carbon dioxide and water. It's not clear if it's feasible economically to do this at a large scale on Earth, but it's definitely an important technology to develop, absolutely critical to make fuel on Mars and for starships to come back from Mars. It has potential to deliver very large payloads throughout the solar system, at least 100 tons. It says 100 plus here. This is actually a little outdated, a couple of years old. Now it's closer to 150. And its capability to do orbit insertion is funded under the NASA Human Landing System. This is a chart that shows the amount of payload that can be delivered to the Moon and Mars by Starship. On the x-axis here is the fill fraction of the Starship. So to deliver 150 tons, which is the maximum capability, maximum Earth ascent capability to the surface of the Moon, a Starship would need to be refueled to 90% of its tank volume in orbit. And for Mars, the number is actually closer to 70%. And the reason is Mars has an atmosphere, and Starship would take advantage of that atmosphere to slow down when it gets to Mars. So it would perform aerobraking, and then it would perform S-turns in the Mars atmosphere, and it won't need its engines until landing on the surface. This chart shows performance for a mission called Neptune Odyssey. It is a proposed mission to be launched on SLS, or Space Launch System, developed by NASA. The green circle here indicates current performance for Neptune Odyssey on SLS, and this purple line is Starship performance. So for the same Earth departure energy, if it were to be launched on Starship, the mission could be approximately twice as heavy, twice as big as on SLS. And there are other orbits that are even more energetic and would allow even more payload to be delivered to Neptune. A quick summary of possibilities for planetary missions on Starship. Starship has several capabilities. For example, it can lower equipment down to planetary surfaces, like a rover here, using an elevator type system. And it also has a capability to carry payloads in its cargo bay and deploy them when needed. So all of this allows a lot of operational flexibility, and some of the possibilities are large and/or multiple lunar rovers, large and/or multiple Mars rovers, significant numbers of Mars helicopters and airplanes, similar to the Ingenuity helicopter that's currently operational on the surface of Mars. Mars sample return is really interesting. Planetary scientists have been trying to get a sample from Mars for a long time now, and Perseverance rover that's currently operational on the surface of Mars is actually gathering samples for return to Earth, and Starship could allow those samples to be returned by delivering a vehicle to the surface of Mars for the return of those samples, or it can itself serve as a vehicle that could potentially return those samples to Earth. Europa Ocean Explorer, which I touched on previously, it would be a mission to get through the icy shell of Europa and get a submersible vehicle into the ocean. Enceladus Orbilander is a high priority mission that was recommended by the Decadal Survey to NASA. It's a survey of planetary scientists who basically rank missions in terms of priority. Enceladus is really interesting. It's a satellite of Saturn. It has geologic activity in its south polar region, has significant plumes of water vapor, and is, like Europa, is also potentially an astrobiological target. Uranus Orbiter is another high priority mission that would be enabled by Starship. Neptune Odyssey that I showed in the previous slide. And I wanted to finish the slide with a quote from a white paper that was published last year that I completely agree with, and that is that NASA must develop a funded program aligned with the development approach for Starship. And I will summarize this presentation with a quote from the Decadal Survey that I mentioned before that just came out. And this is a quote directly from that survey. And it says that planning within NASA needs to begin immediately to prepare for payloads on the first uncrewed Starship flights. And I'll mention a few of my sources here in the acknowledgements. The Heldman et al. 2021 white paper, Accelerating Martian and Lunar Science Through SpaceX Starship Missions, the Decadal Survey, SpaceX Response to Starship Questions, which was provided to me by SpaceX, and the SpaceX Starship User's Guide, which is available on their website. Thank you very much, and I'm happy to take questions.
Thank you very, very much, Dr. Abramov. I really enjoyed your talk. I indulged in interrupting you a few times, and I looked through some of the questions on the side. Jumpgate, you can help me out. But one person going by Call Me Trader would like to know, how do you know that that's water underneath Europa?
That's a really good question. So we had several other spacecraft that have visited Europa and took images of the surface and used spectroscopy to get the composition of the surface. The first of those spacecraft were Voyager 1 and Voyager 2, and that was followed by Galileo, which was a Jupiter orbiter that spent a long time orbiting Jupiter. I think it arrived in 1995, and the mission ended in 2003. And it collected a lot of data on Europa from multiple flybys, and using spectroscopy, he was able to get the composition of the surface, and that turns out to be almost pure water ice. And there are areas on the surface that appear to have experienced flooding, and that also appears to be water ice. So it appears that in some areas of Europa, liquid water came out from underneath, from the ocean presumably, and froze on the surface. And also Galileo had a magnetometer instrument that picked up an induced magnetic field from Europa, which is consistent with the magnetic field that would expect to see from a salty water ocean in the subsurface of Europa.
Awesome. And haven't we also detected trace amounts of water vapor in Europa's atmosphere as well?
I believe that's correct. Yeah, there is I think there's atomic oxygen and perhaps trace amounts of water vapor. Another important thing actually is the observations from Hubble Space Telescope of the plumes on Europa. That's a fairly recent discovery, about 10 years old or so. But Hubble was able to see what appears to be plumes of liquid water coming out of the surface of Europa, presumably through the fractures that were observed by the Voyagers and Galileo spacecraft.
Great. Another question from MM2SS is they're advocating for nuclear power to explore the moon and Mars. What's your view on the role for nuclear power on both the moon and the Mars?
I think it's a very promising technology, but for somewhat longer term, Starship is basically built to go out and explore the solar system here and now, and nuclear propulsion will certainly allow much shorter transit times between planetary targets in the solar system. But it's also it's a technology that has been under development for some time, and it's promising, but it is difficult to develop that technology. Starship is basically built on what we have right now, essentially improving, developing the best engines we could possibly develop. So it's really pushing aerospace, traditional aerospace, to its limits, and creating new paradigms, particularly full and rapid reusability.
Awesome.
Yeah.
Also from Lisa Chandler, she was hoping you could discuss a little bit about what exploring underground on Mars would be like. You have both an exobiology and a geology background, so maybe you could sketch a mission architecture for going underground on Mars.
Sure. So going underground on Mars is really important. If there is life on Mars, it's probably in the subsurface, where it's shielded from the hostile surface environment, from the radiation and things like perchlorates. Mars is still geologically active. It has volcanic activity on occasion. The most recent volcanic activity on Mars was about 1 million years old, maybe even less. And on a geologic time scale, that's really short. So there are probably areas on Mars where there is liquid water deep in the subsurface that's warmed up by latent volcanic activity, and thus hydrothermal systems, which are a really good place to look for life. There are also another kind of subsurface is lava tubes on Mars, which are really interesting in terms of potential habitats for humans, or at least radiation shelters, and are also potentially interesting in terms of astrobiology. So both of those are really interesting. Finding well, we already know areas on Mars that have been active recently, and measuring thermal emissions from those areas and maybe figuring out where the surface or the subsurface is a little bit warmer than it should be would potentially allow us to zero in on areas to drill. All of this, I think, would be really helped with Starship, and especially humans on the ground, because that would be a fairly significant endeavor to drill deep into the subsurface and get samples from there, and do so without any possibility of contamination, potentially introducing terrestrial life into these really potentially delicate ecosystems deep down. in the subsurface. Also, exploring lava tubes is really important, and that can be done robotically. Can also be done by humans. We could potentially have aerial vehicles like drones, helicopters fly into lava tubes and see what's there.
Yeah. Wow. I think that's incredibly fascinating. And both on Mars and Europa, you have a certain level of needing to get through the surface to find out what's below. You have different challenges. On Europa, it's ice. On Mars, it's regolith, and it's a little bit harder. And you have to use different technologies to kind of get down below the surface of each. On Europa, you might be melting through the ice, whereas on Mars, you have to drill through a much harder material that you can't just melt your way through. And I think that's really fascinating about how the different approaches between these two things and what we could find, underneath the surface. It's very fascinating.
Yeah, absolutely. Yeah, we want to see what lurks beneath.
Yeah, absolutely. We do have a little bit more time for any follow-up questions from the audience. If anybody has some burning ones on their plate, maybe we can hear a little bit about the work that you've been doing with Erik as well. If you're willing to share some of that, the two of you could maybe chat on that for maybe 5 or 10 minutes here if we don't have any further questions.
We could do that. I also would like to tease a little bit of a leak. Dr. Robert Zubrin's a big fan of thorium salt reactors in particular. So there is going to be a role for nuclear power on Mars quite soon.
I think that's fantastic.
So Dr. Abramov has been really helping us out a lot by, I got some feedback here. Go ahead and explain. I'm going to put myself on mute. Go ahead and explain your work on the resource layers.
I'm sorry, on what?
On the resource layers, I'm getting a feedback. Yeah.
Okay. Yes, absolutely. There have been a number of robotic missions to Mars. They have returned a lot of data. What I'm mainly focusing on is orbital missions that have performed global mapping and mapped the concentrations of various elements and minerals on the surface, and also things like altimetry, surface elevations, surface roughness, locations of things like lava tubes that might be of interest, and the idea is to convert these data sets into a format that can be imported into the game, so that your location on Mars matters. Different locations on Mars would have different concentrations of resources, like thorium, for example, and that would be incorporated into the gameplay. Hopefully, in an interesting and a compelling way, and it would be rigorously constrained by all the available data from planetary missions.
Yeah, that's amazing. I know our player base is very familiar with the High-Rise program and how we've kind of scraped our surface data and the look of all the plots and really what the game looks like underneath your plot level there. And I think taking that a step further and just kind of mapping out what we already know on Earth is where the stuff is. Where's the lithium? Where's the water? Where's the metals and natural resources? And on Mars and other planets, that's not as well documented. We don't have those data sets as available, and really charting that out and presenting it in this way is such a really interesting and neat thing to do.
Yes, absolutely. That was one of the things that really attracted me to the game, is the use of high-rise DTMs. Actually, the PI of high-rise, Alfred McEwen, was my first advisor in graduate school, and I worked on high-rise briefly as a graduate student. So I was really happy to see that data being used in the game, and I immediately thought about other data sets and how they could be brought into the game. to make a more realistic and compelling playing experience, to have the game basically be more of a simulation of what it's actually like on Mars, and what's needed for human settlement.
That's fantastic. I mean, it must feel it must feel really great to be able to play a game and know that you were part of the process in obtaining that data and getting that into a format that we can enjoy. You can definitely feel like you were a part of this, because you are.
Yeah. Thank you. Yeah, that's like I said, that's one of the things I think that makes this game have so much potential, is that we can integrate real data and make it realistic, make it interesting for the players, and also potentially have the players maybe contribute something to the understanding of the questions surrounding Mars settlement, human Mars settlement.
Yeah, that's absolutely what we're trying to do here. At the very least, it's a thought experiment about what could happen, how it could happen, and what are some of the things that could play out that maybe nobody's ever quite thought of before, when you really put it to practice.
Yeah, absolutely. Yeah, has tremendous potential.
Thank you so much. Eric, do you have any follow-up questions for Dr. Abramov before we call this an hour session here?
So you're on Mars. You're about to go down a lava tube to explore. What's in your backpack? What kind of equipment are you bringing?
Actually, I did go into some real lava tubes in Hawaii when I was there, as part of High Seas, a 4-month simulated Mars mission. So when we went into lava tubes, I had my thermal imager that mapped the temperatures inside the lava tube. We also had a field spectrometer that allowed us to get compositions of materials inside the lava tube. And probably on Mars, yes, some sort of a biological sampling system, a way to collect samples from the lava tube while minimizing the possibility of contamination. We certainly don't want to introduce any earth bugs into that fragile system. I think those would be the top things here: camera, thermal system, spectrometer, and sampling system of some kind.
Yeah, that's fantastic. Thank you for sharing that. It's a little different right now than being able to whip out a tricorder, as some might picture space travel from our fiction, whether how close that might be to reality or not. And one of the other things I wanted to share that I was thinking about is that it is very interesting that the bigger we scale to get these rockets, the bigger systems to places like Europa, the more you do have risk of bringing some of those Earth-like contaminants, keeping those massive engineering complexes sterile and getting that into space. And then, if you're looking for life, that's the last thing you want to do, is contaminate the area.
Absolutely. Yeah, planetary protection is important, and it's something of a question mark now, because like you said, the Starship can potentially deliver a lot of things, including human beings, to Mars, and it's not entirely clear what planetary protection would look like under those circumstances. But it's something that we need to start thinking about for sure.
Yeah. Absolutely. Well, Dr. Abramov, thank you so much for your time.
My pleasure.
Had a wonderful stream. And for everybody, thank you so much in the audience for joining us.
Thank you, Jumpgate, for setting this up.
Absolutely. It's a pleasure to have you both on.
All right. Cheers. Thanks, everybody.
Cheers, everyone. Have a good night.
Thanks.